Last time we ended on this definition. We said that a matrix B is row equivalent to a matrix A if there exists a finite sequence of elementary matrices such that B is the product of these elementary matrices times the matrix A. Let's look at an example. Let's show that B and A are row equivalent. That means show that B is row equivalent to A and A is row equivalent to B. We're going to show B is row equivalent to A first. And that means we can write B as a bunch of elementary matrices times A. And I don't know at this moment how many elementary matrices I'm going to need, so I'm just going to put K for some number that corresponds to this matrix A. So I'm going to look at this matrix A and I'm going to ask myself, what do I need to do to this matrix to get it to look like matrix B? Let's see. The third rows are the same, so I don't have to do anything there. The second row, all I have to do is multiply this row by 2 to get the second row here for B. And for the first row, notice that if I subtract row 2 from the first row, I actually get the first row for B. So let's write what A is down here. So A is 2, 1, 2, 0, 1, 1, 3, 1, 4. And I'm going to use my elementary row operations to transform A to B. Okay, so the first thing I think I'm going to do is I am going to subtract row 2 from row 1. I'm going to write that here. And this is going to correspond to this elementary matrix E sub 1. Okay, so we're going to get 2, 0, 1, 0, 1, 1, 3, 1, 4. And then my next step is I'm going to multiply the second row here by a 2. So I'm going to take 2, multiply it with row 2, and that's going to correspond to E sub 2. So I'll get 2, 0, 1, 0, 2, 2, 3, 1, 4. And this is actually the matrix B. So I only need 2 elementary matrices. And these elementary matrices, we can write them out. So E sub 1. So we took row 2, we multiplied it by a negative and added it to row 1. This is going to correspond to a type 3 matrix. And we're going to have 1, negative 1, 0, 0, 1, 0, 0, 0, 1. So we took row 2, multiplied it by negative 1, and added it to row 1. And then E sub 2 is just 2 times row 2. So we have our 2 elementary matrices. And this one corresponds to a type 2 elementary matrix. So B is E sub 2 times E sub 1 times A. If you want, you can write these out and double check. You get that E2, which is 1, 0, 0, 0, 2, 0, 0, 0, 1, times E1, 1, negative 1, 0, 0, 1, 0, 0, 0, 1, times our matrix A. If you multiply these 3 matrices together in this particular order, you should get B. And you can double check this. I think that would be a good idea for you. Okay, so here's a question. Does the order of these matrices matter? So could B be E1 times E2 times A? Could I move these matrices around, these elementary matrices? And the answer is no, I shouldn't do that. In fact, the order does matter, and it's really important because we can see what will happen in this particular example. So let's say that we take A, which was 2, 1, 2, 0, 1, 1, 3, 1, 4, And let's multiply it by E2. And E2 was multiplying the second row by 2. So let's do that. So what's going to happen when you multiply these two, so this is E2 times A, you're going to get 2, 1, 2, 0, 2, 2, 3, 1, 4, which is almost what we want. But then if we take this matrix and we multiply it by E1, E sub 1, so let's write that out. What's going to happen is you're actually going to subtract this 2 times row 2 from row 1. And you see that we get 2, negative 1, 0, 0, 2, 2, 3, 1, 4, which is not equal to B, because B was this matrix up here, 2, 0, 1, and notice that I have a negative 1 and a 0 here, because we're subtracting this row, 0, 2, 2, not 0, 1, 1, from row 1. So the order does matter, so you have to be careful. So does the order matter? Yes, and you need to be extremely careful in the order that you write it. And how you're going to write it, how we're going to remember this, is that the first thing you do to the matrix to start changing it is the first thing that's being multiplied with that matrix A on the left. Then you can see the second thing goes here, and so on. All right? So we wanted to show that A and B were row equivalent. So here we've shown that A is row equivalent to B. I'm going to leave the part where you show A is row equivalent to B. So we showed that B was row equivalent to A. I want you to show that A is row equivalent to B. You should have 2 elementary matrices. And in fact, what's going to happen is you're going to get the inverses of the elementary matrices that we found. So they're not going to be the same elementary matrices. What you're going to have is A is equal to some E2 prime times E sub 1 prime times B. But these primes just mean that it's not the same matrices as the ones that we just saw. And so what you're going to ask yourself is, how do I get B to look like A? And if you do the problem correctly, you should get that E1 prime is this matrix, and E2 prime is this matrix. So double check that and see if you can get these answers.